We have today another class continuing talking about numerical methods for supersonic flow. Last time we discussed about method of characteristics. What is this method and how it can be used? You saw that method is based on the solution of potential equation for supersonic flow with several assumptions and simplifications, where we could build both mesh, computational mesh, and flow solution at the same time. Today we study a finite difference method, some elements, introduction to finite difference methods, which would help you to understand the basics of such approach. It's implemented nowadays in most of CFD software. If you would like to know in depth about these methods, please read the books which I recommend in the literature, mostly Anderson, Fletcher, Tannehill, Computational Fluid Dynamics and Heat Transfer, and other books which I also put in Apprender 3. So let's talk about finite difference method. Probably you already know a lot, so I will repeat some part which would, I hope, complement your knowledge. Finite difference method is built on transformation of differential equations to algebraic equations, or algebraic equation systems. Depend on method we choose for solution, we obtain or a list of equations, or we obtain an equation system where all these equations are related one to another, depending on our choice. Also, if we look at simulation software, we have also control under this aspect in case of implicit model. Once we choose a solution, for example, in Fluent, implicit model is list as a set of equations not connected in one system. And in case of explicit solution, explicit method, it's a set of equations which are related inside one system, inside system. What to choose is every time it's a choice of complexity and speed of calculation. But in most cases, explicit solution methods are better because they allow to have higher integration time step, much higher integration time step. We're talking about tens or hundreds of times more faster calculation. So explicit calculation is better. I hope it's explicit calculation. If I'm not wrong, let's look after in the book and check. Here on formula 27, 28, and 29, you can see how derivate from our flow equations could be substituted in algebraic model by algebraic relations. On the left side is derivate around some arbitrary point ij in a bidimensional space. I is coordinate on x direction and j usually is coordinate on y direction. So this arbitrary point in space, if we visualize, we would see in x direction axis, we will see that there is a point of central uij, and the next one ui plus 1j, previous one ui minus 1j, coordinates 3 different points. They are written in a way you see here on these formulas. They are applied for constant distance between points. So it's everywhere delta x distance. As you know, expressions written on the right part of these equations are simply called approximation of derivate, the approximation of first order. of derivate, and this third one, the third equation 29, is approximation of second order. You may ask one question, which approximation between these three we should use in our flow equations. It always depends on equation type, or on the equation which we are solving in our system, and also depends on process we are calculating. For example, for velocity, positive velocity going in the positive direction, we use second equation. It's rearward difference are more typical. This works in the following way. We know all parameters which happened before in space, and if we would like to calculate next parameter, some parameter with the coordinate aj, knowing all previous parameters, calculating from left to right, we use previous parameters to calculate derivative in point where we are interested in. In opposite, when flow is going in a different direction from right to left, the forward difference is better, because we know points on the right, okay, and to calculate point of our interest, we use all points on the right when flow is going in this direction. It's not just of velocity direction, but also of velocity of perturbations. There are different forms of equation systems where we express flow equations in terms of perturbations, and depending to which direction perturbation is going, we choose one or another approximation, equation 27 or equation 29, depending on where perturbation is going. This algorithm usually takes into account that perturbation can go in any direction. So, for example, if I'm saying that first equation is telling to us that perturbation is going to left direction, and second one, perturbation is going to right direction. Okay, we can write in general that real derivative which we would like to use in our equation system would be du by dx would be some coefficient alpha multiplied by du by dx calculated on the left direction plus alpha minus 1 derivative calculated du by dx on the right direction. So this is how usually is approximated in real solution once we are solving, for example, an ANSYS fluent. And then ANSYS is determining, or program is determining where flow perturbations are going. For example, flow perturbations are going to the left, from right to left. So in this case, alpha will be equal 1, okay, and derivative will be just this here. In case when perturbations are going to the right, we can define that alpha is equal to 0. So our derivative will be calculated just using the right side of this relation. So this flexibility usually realized in any simulation software, implementing all possible configurations of flow perturbation going in different directions, and we already can, inside the same model, implement such process. So our program would be not dependent on direction of flow or direction of perturbations. It will automatically adapt according to definition of alpha at one or another point. This is typical feature. Equation 29 is a bit different. As you can see, this is central difference definition of derivative, and it uses usually when flow is dissipating, or let's say some parameter is dissipating, for example, heat. Heat dissipates in all directions independently on, we're talking about convection, calculation of diffusion. Diffusion happens in all directions. So here in this case, central difference method is better. It's a second order method which has additional accuracy with respect to equation 27 and 28. Equation 29 is more accurate, but it can be used only for method which is going in all directions equally, or for flow solutions which are using some specific tool to mitigate or to calculate, let's say, some correction of flow. This, what I'm talking about, we will see very soon. Very soon. So depending on flow direction, depending on type of process we are calculating, depending on parameter we are calculating, we use forward difference, rearward difference, or central difference. These three equations are not the only options which we might have to approximate our derivatives in terms of points, to transform differential equation to algebraic equation. There is a huge number of such relations which you, for example, might find in Anderson-Pletcher-Tannehill, which I recently suggested you to study together with CFD methods. There you can see that first derivative can be approximated using not just 2 points, but also could be used by 3 points, 4, 5, 6, and 7. More points you use for approximation, theoretically better is precision of calculation of derivative. Because, for example, when we are using just 2 points, like equation 27, we have 0.1, 0.2, and we calculate our derivative somewhere as a line. If we have already 3 points, we have a parabolic function. Okay, this is the third point. We have a parabolic function. So our estimation of derivative at any particular point would be more accurate. If we have 4, 5, 6 points, we increase complexity of calculation, and at the same time we increase accuracy of calculation. Also, not just the complexity of approximation or order of approximation here is important. We need to take care about additional problems and physics of such approximations. One example I could give you here is the following. For example, we are approximating temperature distribution using 3 points. How it can be done? 3 points. Okay. Sorry. Please let me know if you have questions or comments today. You can see your comments and I can read them during my discussion. Let's assume we have 3 different points. Distribution of temperature. It's heat. We have temperature 1 heating from this side. We have temperature 1, then we measure temperature 2, or we calculate temperature 2, and then we calculate temperature 3. Temperature 2 and temperature 3 are same. Temperature 1 is higher. So we started to heat from this bond here, started to add the heat, and we calculate how our heat is distributed inside space, inside gas or inside solid, no matter. You know that once flow is not moving, gas and solid have same equations to calculate heat dissipation. Let's assume we have T1 higher and T2 and T3 are same. So if we use just linear approximations, which I showed you with these dots, we have no problem from physical point of view that the temperature is changing from one point to another according to this linear function. Of course, it's not realistic, right? It's not real temperature distribution, but this is simplest possible approximation of temperature distribution which we could accept. Let's imagine that we would like to increase precision, and we would like, instead of line, use just parabolic function. This happens in many cases. Okay, 3 points, why not to use parabola? And I will draw you parabola, right? Going through these 3 points, you know that analytically you can calculate equation of this parabola. Can define exactly how it goes by 3 points, because 3 coefficients inside parabolic functions we have corresponding to 3 points that we know. So equations can be defined. What is the problem in this case? The problem is that between point 2 and point 3, we already have a difference between first order approximation, linear function, and second order approximation, parabolic function, which is correct. Which is correct in this case, parabola or line? The answer is line is better, because physically, if we heat from one side, we add heat and temperature 1 is increasing. Between temperature 2 and temperature 3, temperature could not decrease. We cannot extract heat by adding heat from another side. So if we have in the middle, let's say temperature 4 would be smaller than temperature 2, and temperature 4 would be smaller than temperature 3, it's totally wrong from a physical point of view, because temperature cannot decrease in between points without any reason. But just because we substitute our function from linear to parabolic, we start having this computational problem. So using more points for approximation is sometimes good, but sometimes very dangerous, because you overestimate or underestimate this process. We can have something similar for another temperature distribution. I like temperature because we understand how temperature is going. You know, heat is distributed from one part of body to another part of body, inside gas or inside solid, no matter. Here we do not account in flow, right? But even if we would have flow in this picture, we could, by any possible way, could not have lower temperature than the lowest in point 2 or point 3. Another example, for example, we will not heat, but we will cool. We will cool down. This is our boundary here. And I had constant temperature, temperature 1, temperature 2, constant temperature 3. I start to cool down. I start to decrease. So bilinear function is like this. And by parabolic function is overestimating. So if I start to cool, I extract energy from temperature 3. By approximation of parabolic function, we have increase of temperature between point 1 and 2, which is totally wrong. It cannot happen. By extracting energy, you cannot increase temperature at any specific point. This is non-physical solution. This is happening only because we substitute our time derivative in our equation of heat transfer by a wrong in a wrong way, let's say, not by a wrong function, because there are methods to compensate this problem. Approximation by line is called first order approximation, and you can find in solution methods when you use ANSYS Fluent, you already remember, right? That you can choose first order approximation, second order, third order, etc. So first, second, and third corresponds to an order of polynomial which approximates your derivatives. This is why I do not always like when people choose second order approximation, because you can overestimate or underestimate flow properties. This doesn't happen always. There is a way to compensate this error inside Fluent, but should be really carefully used this method. First order approximation is not so accurate, but it's much faster to calculate, and it does not have this problem. this problem. I hope more or less clear. Let's go further. Our equation system. This is just an example Anderson shows. I will not explain again what are these equations. Probably you saw them so many times already. We see that there is no time derivative. So equations are stationary, right? So we use only approximation of space derivatives. In the same way that was presented on previous slide, we take each of these derivatives and we write, instead of derivative, we write this algebraic expression relation between points. And we transform all our equations, differential equations at each point to a list of algebraic equations, or it will be system or just the number of equations you solve one by one. Do not forget, we always must complement equation system to have same number of unknown that is equal to number of parameters. Here, equation of state and internal energy equations are required to provide this solution. Okay, some transformations is not. I would not like to stop on these transformations. I would like to remind you that I present you not all information that Anderson says. It's almost impossible to repeat in a reasonable time. But I strongly recommend you to read the book and to read additional literature to understand deeply, if you would like to work with simulation, to understand how these simulation methods were developed, so you will be not like a monkey pushing buttons, but with the already theoretical knowledge, you will choose methods that you really need and choose options that you really know how they work and why you do it. All decisions in aerogas dynamics, same as in engineering science, they are all justified or by previous experience or by references or by any other reason, some suggestions, some justifications. Here, same. One way to improve quality of solution is to make transformation of coordinate system, which you can see here on figure 8. It shows to us that there are two spaces. Actually, program of simulation, CFD software nowadays, most of the software is using transformation of coordinates. Fluent does it in a very, very efficient way. So there is a physical plane or physical mesh which you are building around your body. You did it for airfoil previously, now you do it for diffuser and nozzle. So mesh is always curved. Mesh is changing according to shape of the body. Here in example A, physical plane, we have calculation inside the nozzle. We have two edges. One edge is nozzle shape, nozzle wall, and the lower part is the axis, okay, or axis of symmetry or axis of rotation, no matter. So we have limited our space inside the nozzle or inside volume we are simulating. According to the shape of this space, we construct our mesh, as may seen here, right? Cells at the inlet, probably this is the throat where flow will start, will be smaller, not so high, right? And since number of cells is equal on entrance and the exit, also will be same number of cells. These cells would be bigger. And because of this, all cells would be different. There are no equal cells in this calculation. So we cannot use directly definition of a derivative, for example, taking two discrete points and calculate and calculate derivate. For example, if I'm looking on point, this one here, central point, and the next point, and if I will try to write that my du by dx would be equal to ui plus 1j minus ui minus, uij divided by delta x, this would not be correct anymore. For this approximation, which I'm having for current mesh, I needed to recalculate. I need to transform my coordinates, and then I would be able to use approximation of derivatives. Such transformation, I hope you studied in mathematics, is called transformation of coordinates, is made by introducing of Jacobian of transformation, and in such way we always can represent physical plane as a computational plane. It's identical from point of view of number of points, from point of view of relation between points, but it already will be structured and it will be equally spaced. So for this case, if I will write, for example, du by dxc would be equal to u, okay, I plus 1j minus ui j divided by delta c. Okay, this would be correct now. So first, before calculation or before solving our equation system transformation to algebraic equation system, we must do transformation of coordinate system. After we transform coordinate system, we can easily rewrite our derivatives inside equations in a simple way. We solve our equation system in such way, and then third step, we make reverse transformation and we go back to physical plane, not to this equation. We go to physical plane. So transformation to receive computational plane, write equations, solve equations, transform to back to physical plane and visualize. This is what Fluent and other software are doing once you run simulation. Run simulation. This transformation of coordinate system is done automatically. It is a process of calculation of transformation coefficients for each cell, for each relation between cells. It's usually linear coefficients which we must put inside our equation system, which provides such transformation. Anderson also shows how to make transformation for simple case, which I just showed you for the nozzle. I will probably not pay so much attention to this. Just few words. Transformation is done in the following way. We define a new coordinate system, xi and eta, which you can see on equation 47a. These two coordinates are defined as function of x and y. According to direction of the nozzle, x would be same as xi. Linear dimension is not changed because physical plane and computational plane are having equal spaces in x direction and xi direction. And in eta direction and y direction, between them we have relation. We have relation which describes shape of the nozzle. In such a way, we will write analytically what is relation between derivatives for original coordinate system and for transformed coordinate system. This is shown on equation 48 and 49. We see that the derivative of any derivative of x can be expressed as function of xi and eta, and any derivative direction of y can be also expressed as function of xi and eta. And then we take all parameters which we have in our equation system and we rewrite this equation system in transformed equation system. Here you can see such result of transformation. So actually we are not solving our original flow equations. We are solving transformed flow equations, which we might see on this slide from 50 to equation 53. We solve this equation system. Here in these equations, some parameters, they are actually constants when we go from equation in derivatives to equation algebraic. For example, these parameters here, these derivatives, they are simply coefficients, right? For each specific point, they are different coefficients. So we, as I already told you, we multiply our right part of equation by some coefficient which is different for each point, representing transformation from physical plane to computational plane. So computational, this is not hard. And if some of you would like to study how to do it, you can open same book of Anderson, Pletcher, Tannehill, where they show step by step how this transformation can be provided and how can be calculated with examples such flow in the nozzle. If you would like to study in deep CFD methods, this is obligatory to know when you work with the numerical flow simulation. Okay, then solution. Solution is obtained in the way that, in the simple way that you can see on equation 54 A to D for all flow parameters. Here, F, G, H, K are flow vectors of flow parameters. Definition of these parameters was here. Okay. They are just right sides of flow equations of continuity F. Okay, let me see. F and G. No, F corresponds to continuity, G and H corresponds to momentum equation, K corresponds to energy equation. Right side of these equations. And these right sides of equations can be found numerically in the way that on the previous step, we have just increment of flow parameters, right? For example, on continuity equation, new parameter of new right side of continuity equation can be calculated as old value of this function plus some average derivate multiplied by step on X. Okay. Once we, it's a simple, can be called as simple series, right? Simple series of first order. The same process we are doing for all flow properties. For example, for momentum equation, for energy equation. How we transform after from right side of equation to the value of function is also not so difficult. For example, f function. Okay, let's see. If we divide one by another, let me go back to the definition. If we divide one by another, for example, we divide g function by f function, we will obtain probably v component of velocity, right? Right, and then combining these relations, we obtain all flow properties, all the rest flow properties. Probably next time I will show you from Anderson, Pletcher, Tannehill this transformation. Now for today's lecture, I did not prepare. Such solution of flow equations is usually done in two steps, in two stages. Stage one is called predictor step, where we predict our derivatives and predict flow properties, like preliminary calculation of flow properties. And second step is called corrector step, which is more exact calculation of derivatives and flow properties. Predictor corrector step is a typical strategy to solve flow equations. For example, on predictor step, we can write that any equation we are taking, for example, F equation, continuity equation, new value on continuity equation function would be equal to the old value plus derivative multiplied by step, right? Where this derivative can be calculated by the equation, like relatively simple equation. Here, transformation of coordinates, the first one, first component. Then this second component is a derivative on calculated from point j plus 1 and j. So it's forward derivative. This one here, forward derivative. And the second part, which is related to our transformation of coordinates, since we have we are calculating it according to modified equation system. We also calculate this part here. This part here also by forward derivative. We will see that we take parameters at the next point j plus 1 and at point j. In such a way, we calculate flux flow rate, right? Flow rate. Having predictor, calculating by predictor step, there are several methods. It's not the only possible method. This is an example of many different methods. I would like you to understand that there are many methods to calculate predictor step and corrector step. The main idea is to find approximately derivative of every function present in our flow equations. Opening the book, we can find many of these functions, of these ways to calculate. And corrector step is correction of previously calculated derivative. How it's done, for example, taking previous equation which we saw, we will calculate the average derivative as 1/2 of sum of derivative calculated between two different points. Okay, we have the previous previous point from corrector. Okay, this with one line with corrector. With predictor, with first step, and then we have we are using this same logic to calculate for corrector step. We are calculating df by dxt at let's say at next step. And the average derivative we are obtaining is a half between predictor and between corrector. Average is always good. For example, having 2 points, which point is more correct? Something that happens in the middle. These 2 points are same points in space. They are not different points in space, same points in space. So between same points, same space, we are having better accuracy, second order approximation, if we calculate in this way. I see no question for now. I would like to talk about time-dependent techniques, something which is related with time. Now we will have time derivative and some idea related to time. Another example is flow around blunt body. You probably remember that blunt body is a body which creates bow shock wave. Flow is supersonic, Mach number higher than 1, as you can see on physical plane. Is shown body shape. This is solid body here, and flow going against this shape, creating a shock wave. We can build computational mesh between shock wave and a body. And then we can transform this computational mesh to a physical plane, to computational plane. And calculate flow property of our equations for computational plane, make reverse transformation. This is also typical example. Is one particular example, I think, quite old, when computational resources were very limited. You see that mesh is rough, but such approach allowed to calculate flow properties, change of flow properties between shock wave and the body with quite acceptable precision. In real calculation, of course, you know that number of points is much bigger than presented in this schematic. It's just a schematic. Here, the problem is to find the shape of a shock wave. How precisely we can calculate shape of the shock wave will depend on quality of final solution. Shape of the shock wave could be calculated by several methods. There are methods predicting it analytically. And probably I already told you that there is one report of NASA which is saying how to calculate behavior and distance between shock wave and the physical body. This model is quite complex, but theoretically it allows to provide such calculation. Why is important to calculate shock wave around the body before numerical simulation, or at least to know shape of shock wave before simulation? Because before shock wave here at m infinite, all flow properties are constant. So from computational point of view, there is no sense to calculate anything outside of this shock wave. Only between shock wave and the body, flow properties will change. Everything which happens before shock wave will have constant behavior, constant flow properties, totally constant flow properties. This is why, since in many applications we would like to optimize computational time and complexity, we would like to know this shock wave. Shape of shock waves, as I told you, can be defined by empirical methods or complex analytical methods, for example, published by NASA. But also shape of this shock wave can be calculated approximately by preliminary numerical simulation. If we define a mesh in a zone bigger than shock wave, for example, if we extend the mesh, let me try to represent for you something like this. If we build a mesh bigger than we need, okay, we don't know where is exactly the shock wave, so we make always bigger simulation. And we define our boundary conditions inlet before shock wave. This is the way how we do calculation in our supersonic diffuser in work too, right? We don't know exactly how, we know approximately, but we don't know exactly how oblique shock wave will be placed in space. So we simulate bigger volume inside this volume, our shock wave will be established. And when we have this preliminary simulation made, we can save a lot of computational power, or we can improve significantly quality of solution once we will move all these or remove or move these nodes inside space between shock wave and the body. Or simply removing this part of mesh, we can save a lot of computational power, and we can save a lot of time for simulation. For two-dimensional flow, this is not very typical because two-dimensional flow converges relatively fast, but for three-dimensional flow, this could be extremely, extremely important when we can save thousands or even millions of cells which have no contribution to solution, which are just staying inside simulation. Even if cells are somewhere here at constant flow part, they are still calculated. Calculation happens in all cells, even though if all flow parameters are constant and same everywhere. This takes space in memory of computer, and this is calculated from one iteration to another. So to decrease or remove useless cells is a very important task for any numerical simulation. In previous decades, 30, 40 years ago, it was necessary and it was obligatory part of work because computers had very limited amount of memory and computational resources. Nowadays, probably not so much important to remove, but I always ask that if you would like to obtain good quality solution, you must create nice looking simulation, really nice looking simulation without any totally useless parts. So this is how the strategy of mesh building for blunt body should be made. We make preliminary simulation, and then we adjust mesh according to shape of the shock wave. Then program is making for us transformation from physical plane to computational plane and solves not equations of flow, but algebraic equation system. Some solution represented here. Anderson also explains some details on the solution. You can see that streamlines are curved. For blunt body, it always happens. It's very typical for rotational body that after shock wave, streamlines are not having straight direction. They are always curved, especially in the part of subsonic to supersonic transition. Another aspect you can see here that we can determine change of entropy inside such flow, that at point A, which is point of streamline going exactly to stagnation, here we will have a maximum entropy or maximum possible entropy change in our system, and all points which are far from this stagnation streamline. Let's say stagnation streamline is a streamline which leads to stagnation point. All lines, more far you are from this streamline, smaller would be the entropy on this streamline. Just this observation. Another computational model. Now this computational model consists of two parts devoted to time or time derivative, and devoted to space, changes of parameters in space. So it's a transient transient model, where all flow properties change not just in space, but also during time. Convergence of such equation system can be a long process. We already know, right? Simulating airfoil, we can choose, or it will be transient or stationary. If you choose transient, you will see that convergence, which is shown also on figure 11, is not a fast process. You can observe decrease or increase of residuals. Here on figure 11, parameter is different from residuals. It's not residuals by itself. It's some flow property or stabilization of flow property in time. And residuals, which ANSYS is showing, is a derivative. It's a derivative of this curve. So when it goes to steady state, residual is 0. Residual is difference between different time steps of each flow property. For example, mass residuals of mass is difference between densities between two different time steps divided by time step. Delta T is basically time derivative, dimensionless time derivative. And here, dimensional flow property, some velocity, for example. Velocity can increase, can decrease, but if process converges on steady state, will be a constant value for each point. This parameter we can observe, or such behavior we can observe for all points in space. Each point has its own convergence process, right? What we see in residuals in ANSYS Fluent is a maximum value of this behavior of time derivative between all possible points in space. There are also methods to calculate based on predictor-corrector step. In predictor step, you can see how, for example, density is obtained. Density on new time layer would be equal to density on old time layer plus derivative by time multiplied by time step. And corrector step is utilizing density calculation in two different time steps. Density derivative on not two different time steps, on parallel, let's say parallel time steps. Density calculated on by one method and by another method. Taking average gives us more improved density derivative as final. Convergence from point of view of behavior of shock wave is shown on figure 12. Here we can see also a blunt body and the position of shock wave at different time moments. I don't know about 0 delta t. It's probably exaggeration, because such 0 delta t can be calculated only by some analytical or empirical method, right? Shockwave cannot be obtained on initial time step before simulation. So probably it's first simulation time step, or close to first time simulation. Then after 100 time steps, our shock wave would be moved with respect to initial one. After 200 time steps, as you may see here, this movement of shock wave slows down. It moves a little, right? And between 200 to 300 time steps, it will be even more smaller difference. Right? So it slows down, and shock wave becomes more and more stationary. So time derivative or parameter related to time derivative becomes smaller and smaller from one step to another. Shock wave stabilizes. between 300, 400, and 500 steps, we see no difference. It means that we are close to stationary flow and we can finish calculation according to our stability criteria, stability by mass, momentum, or energy, or any other stability criteria which we can imagine. For example, drag coefficient also can serve as stability criteria. Graphical representation of stabilization. This is stagnation pressure used as stabilization criteria. Also, as one of possible parameters, we can see variation of stagnation pressure. Or it's forgot this word, sorry. Relative stagnation pressure relative to infinite pressure, because we must have some reference point. And with the time, at first time steps, it changes, right? At time steps more than 2 already, this change of relative stagnation pressure is smaller and smaller. So from step 4 to 5 and from 5 to 6, especially, extremely small variation. So we can assume that flow is converged. Depend on the goal of your simulation, you can choose different convergence criteria, not just flow equations, but also others. Here on this picture, we see comparison between different methods of calculation or results of calculation on cylinder, numerical simulation, CFD, and Newtonian method is the method which we will discuss in chapter of hypersonic flows. Newtonian method is an empirical method or approximate method allowing to calculate pressure distribution on cylindrical bodies or bodies which are having mostly pressure drag, let's say. Okay, we see that for simulation and empirical approximation by Newtonian method, results could be close, not exact, but close. They are not exact because models are totally different for both of these methods, but they are it is possible to compare and see more or less behavior or similar behavior between these two methods. This is how we can justify or simulation, or we can justify empirical method. Usually, empirical method is based on experiment already. So in many cases, it can be more accurate than simulation. But again, depending on how this empirical method was built, based on what? Based on simplification of flow equations or processing of experimental data. Anyhow, it is always good to have comparison between different methods of solutions to have more confidence about results of calculation, and it will be always welcome in engineering work. Different methods. Please use different methods when you design some structure. Do not trust on just one method of calculation or one solution you obtain by using just one possibility. There are always a lot of possibilities to validate, and validation is extremely important because it proves that your solution is correct. Figure 15 shows different shapes and sonic lines for parabolic cylinder. That shape we seen before on previous picture. For different infinite Mach number, these figures are obtained by numerical simulation. we see that for smaller Mach number, of course, we have bigger distance between cylinder and shock wave. And when we increase Mach number, our shock wave becomes closer to a body, right? Same time, once we increase Mach number, this size of subsonic region becomes smaller because we have more energy inside flow. So size of volume with a relatively small velocity also becomes smaller in this case. Just observation, such pictures we can easily obtain by numerical simulation of inviscid compressible supersonic flow. One important observation here is that all results we see today are devoted for inviscid flow. There is no boundary layer, no viscosity. So all flow models are simplified with respect to viscous flow models. Okay, that's it. We finished part 13. Please let me know if you have some questions. I can wait 1 minute, and I'm expecting to answer your questions if you have some. And next time we will meet on Tuesday. We can start chapter 14 already. I can wait 1 minute, please. Let me know if you have questions. There is one part missing from my presentation. I don't know where it's gone, but I hope, because probably I opened old version of my presentation. There is missing a part devoted to flow around cylinder. Oh, sorry, flow around conical bodies. I wanted to present here, but I do not see anymore this information. Probably it's in another version of my presentation. I will try to compensate next time. On Tuesday, we will go back to question of flow around cylinder. I will find my presentation. And I will show you also aspects of flow simulation or flow process around conical bodies. I don't know why this part is not here. I see it's very important. We will pay more attention on this question before going to hypersonic flow. Chapter 14 is talking about hypersonic flow. I also will introduce you some concept, recommend some literature, and I hope you will have some questions to ask.